Tonight, we're talking about one of humanity's most remarkable achievements, a spacecraft that's been traveling through space for nearly 50 years. Voyager 2. It's moving away from Earth at roughly 34,000 miles per hour. It's already left the solar system. It's crossed into interstellar space, the region between the stars where the sun's influence finally ends. And it's still going. Still sending data back across billions of miles. But here's what most people don't realize. Voyager 2 isn't going to travel forever. It's going to die. Its power is running out, degree by degree, year by year. And when it finally goes dark, it will be in a very specific place in our galaxy, drifting on a trajectory that was set the moment it launched from Earth in 1977. By the end of tonight, you're going to understand where that place is, where Voyager 2 is heading toward after it goes dark, and what will finally silence one of the most extraordinary machines humanity has ever built. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Voyager 2 is currently about 13 billion miles from Earth. That's roughly 140 times the distance from Earth to the Sun. Light from the spacecraft takes more than 19 hours to reach us. When engineers send a command, it takes roughly 40 hours for the signal to travel there and back. The spacecraft is moving at roughly 34,000 miles per hour relative to the Sun. That sounds fast, and it is by human standards. But on the scale of interstellar space, it's incredibly slow. At this speed, Voyager 2 covers about 1 light-year every 18,000 years. The spacecraft launched on August 20th, 1977, 16 days before its twin, Voyager 1. The mission was designed to take advantage of a rare alignment of the outer planets that occurs once every 176 years. Jupiter, Saturn, Uranus, and Neptune would be positioned in such a way that a single spacecraft could visit all 4 using gravitational assists. Each planet's gravity would accelerate the spacecraft and bend its trajectory toward the next target. Without this alignment, visiting all 4 planets would have required decades of travel time and massive amounts of fuel. The Voyager missions were humanity's grand tour of the outer solar system. Voyager 2 reached Jupiter in July 1979. The encounter revealed details about Jupiter's atmosphere, its great red spot, and its moons. The spacecraft discovered active volcanoes on Io, the first active volcanism found beyond Earth. It revealed Europa's smooth, icy surface, hinting at an ocean beneath. It captured images of Ganymede and Callisto, showing their ancient, cratered terrains. From Jupiter, Voyager 2 flew on to Saturn, arriving in August 1981. The encounter revealed the intricate structure of Saturn's rings, showing thousands of individual ringlets separated by gaps. It studied Saturn's atmosphere, measuring wind speeds of up to 1,000 miles per hour. It flew past several of Saturn's moons, including Titan, though that moon was Voyager 1's primary target. After Saturn, Voyager 2 continued to Uranus, becoming the first and still the only spacecraft to visit that distant world. It arrived in January 1986, after nearly 5 years of travel from Saturn. The encounter revealed Uranus as a strange, tilted world. The planet rotates on its side, with its axis tilted 98 degrees relative to its orbit. This means Uranus essentially rolls around the Sun like a ball, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Voyager 2 discovered 10 new moons and revealed details of Uranus's faint ring system. It measured the planet's magnetic field, which is tilted 60 degrees from the rotation axis and offset from the planet's center. The spacecraft's instruments detected a strange, asymmetric magnetosphere, unlike anything seen at other planets. From Uranus, Voyager 2 flew on to its final planetary target, Neptune. It arrived in August 1989, 12 years after launch. The encounter revealed Neptune as a dynamic, stormy world, despite being so far from the Sun that it receives less than 1% of the sunlight Earth gets. The spacecraft discovered the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, but darker against Neptune's blue atmosphere. It measured wind speeds of over 1,200 miles per hour, the fastest winds detected on any planet in the solar system. It discovered 6 new moons and revealed details of Neptune's rings. The encounter with Triton, Neptune's largest moon, was particularly remarkable. Triton is the only large moon in the solar system that orbits its planet backward, moving in the opposite direction to Neptune's rotation. This retrograde orbit suggests Triton wasn't formed alongside Neptune, but was captured from the Kuiper Belt. Voyager 2 discovered active geysers on Triton, plumes of nitrogen gas erupting from the surface and reaching heights of 5 miles. This made Triton only the second body in the outer solar system, after Io, known to be geologically active. The temperature on Triton's surface is minus 391 degrees Fahrenheit, making it one of the coldest surfaces measured in the solar system. The encounter with Neptune was Voyager 2's last planetary visit. The gravitational assist from Neptune sent the spacecraft downward relative to the plane of the solar system, out into interstellar space. But the mission didn't end. Voyager 2 continued operating, sending back data about the outer reaches of the Sun's influence. The spacecraft carries 10 scientific instruments, each designed to study different aspects of the planet's and space environment. The imaging system consists of 2 cameras, a wide-angle camera and a narrow-angle camera. These cameras use Vidicon tubes, a technology that was state-of-the-art in the 1970s, but is now obsolete. The cameras captured the iconic images of Jupiter's Great Red Spot, Saturn's rings, Uranus's moons, and Neptune's Great Dark Spot. The images were transmitted back to Earth, one line at a time, each image taking minutes or hours to transmit, depending on the spacecraft's distance from Earth. The plasma science instrument measures the density, temperature, and velocity of charged particles in space. This instrument was crucial for detecting the heliopause crossing. It measured the solar wind throughout the journey and detected when the solar wind disappeared and was replaced by the interstellar plasma. The magnetometer measures magnetic fields. It detected Jupiter's enormous magnetic field, the tilted magnetic fields of Uranus and Neptune, and the transition in magnetic field orientation at the heliopause. The cosmic ray detector measures high-energy particles from deep space. These cosmic rays are primarily protons and heavier atomic nuclei accelerated to nearly the speed of light by supernova explosions, pulsars, and other energetic events in the galaxy. The detector measures how many cosmic rays are hitting the spacecraft and what energies they have. This helps scientists understand the radiation environment in interstellar space. The low-energy charged particle detector measures particles with lower energies than the cosmic ray detector. It studies electrons and ions near the spacecraft, helping to characterize the plasma environment. The Planetary Radio Astronomy Instrument detects radio emissions from planets and from the interstellar medium. Jupiter emits powerful radio bursts generated by its magnetic field. The instrument detected these bursts and helped map Jupiter's magnetosphere. The ultraviolet spectrometer measures ultraviolet light from stars, planets, and the interstellar medium. This instrument helps study the atmospheres of the outer planets by measuring which wavelengths of ultraviolet light were absorbed by atmospheric gases. The infrared spectrometer measures infrared radiation, which is essentially heat radiation. This instrument helped determine the temperatures of planetary atmospheres and surfaces. The photopolarimeter measures the polarization and intensity of light. This helps study the composition and structure of planetary rings and atmospheres. The radio science investigation uses the spacecraft's radio transmitter. By measuring how radio signals from the spacecraft are bent by planetary atmospheres, scientists can determine atmospheric density, temperature, and pressure profiles. Not all of these instruments are still operating. Some have failed over the years. The photopolarimeter failed in 1991. The ultraviolet spectrometer and infrared spectrometer were turned off to conserve power. But the magnetometer, cosmic ray subsystem, and plasma wave subsystem are still operating, still sending back data about the interstellar environment. These instruments continue to make discoveries even now, decades after the planetary encounters. The Sun creates a bubble around itself called the heliosphere. This bubble is carved out by the solar wind, a stream of charged particles flowing outward from the Sun in all directions at speeds of roughly 700,000 miles per hour. The solar wind consists primarily of electrons and protons, with some heavier ions mixed in. These particles are ejected from the Sun's corona, the outermost layer of the Sun's atmosphere. The corona is incredibly hot, millions of degrees Fahrenheit, hot enough that particles can escape the Sun's gravity and stream out into space. The solar wind is not uniform. It varies with the Sun's activity level, becoming stronger during periods of high solar activity and weaker during quiet periods. Solar flares and coronal mass ejections can send bursts of particularly dense, fast-moving solar wind particles into space. These disturbances can affect spacecraft, satellites, and even power grids on Earth when they reach our planet. The solar wind pushes against the interstellar medium, the thin gas and dust that fills the space between stars. The interstellar medium is even more tenuous than the solar wind, but it's there, filling the space between stars with a thin fog of hydrogen and helium atoms, along with trace amounts of heavier elements. This interstellar gas has its own pressure, its own motion, its own magnetic field. Where the solar wind's pressure balances the pressure of the interstellar medium, the heliosphere ends. This boundary is called the heliopause. It's not a sharp edge, like a wall. It's a transition region where the solar wind gradually weakens and the interstellar medium gradually takes over. The heliopause is roughly tear-shaped, with the blunt end facing the direction of the Sun's motion through the galaxy and a long tail stretching behind. The Sun is moving through the interstellar medium at roughly 50,000 miles per hour. This motion creates a bow shock in the interstellar medium, similar to the bow wave created by a boat moving through water. On the side facing the Sun's direction of motion, the heliopause is closer to the Sun, roughly 90 to 120 astronomical units away. An astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So the heliopause, on the forward side, is roughly 8 to 11 billion miles from the Sun. On the trailing side, the heliotail stretches much farther, possibly hundreds of astronomical units. The exact size and shape of the heliosphere depends on the pressure of the interstellar medium, which varies depending on where the Sun is in its orbit around the galaxy. We're currently passing through a relatively low-density region of the interstellar medium. If we were in a denser region, the heliosphere would be compressed, pushed closer to the Sun. If we were in a less dense region, it would expand farther out. For decades after leaving Neptune, Voyager 2 traveled through the outer regions of the heliosphere, measuring the solar wind's properties as it weakened with distance. The spacecraft crossed the termination shock in August 2007. This is the boundary where the solar wind suddenly slows from supersonic to subsonic speeds as it begins to feel the pressure of the interstellar medium pushing back. The crossing occurred at roughly 84 astronomical units from the Sun, about 7.8 billion miles. The plasma instruments detected the sudden change, a drop in the solar wind's speed, and a corresponding increase in its temperature and density. The solar wind had been streaming outward at roughly 700,000 miles per hour. At the termination shock, it suddenly slowed to roughly 250,000 miles per hour. The sudden deceleration heats the plasma, just like air heats up when compressed. The temperature jumped from roughly 10,000 degrees Fahrenheit to nearly 1,000,000 degrees. The density increased as the solar wind particles piled up behind the shock. Think of it like traffic on a highway. Cars are moving at high speed, then suddenly they encounter a traffic jam. The cars slow down and bunch together, increasing the density of traffic. The termination shock is similar, except instead of cars, it's charged particles. The magnetometer detected changes in the magnetic field at the termination shock. The magnetic field, which had been relatively smooth and orderly in the outer heliosphere, became turbulent and chaotic at the shock. The field strength increased, and the field direction changed more rapidly. The cosmic ray detector saw an increase in cosmic ray intensity. Cosmic rays from interstellar space have trouble penetrating deep into the heliosphere because they're deflected by the Sun's magnetic field. But near the termination shock, where the solar wind is slowing and the magnetic field is weaker, more cosmic rays can penetrate. The detector saw a gradual increase in cosmic ray counts as Voyager 2 approached the shock. Then, a sharp increase right at the crossing. Beyond the termination shock lies a region called the heliosheath. This is a turbulent zone where the solar wind has slowed but hasn't yet stopped. The solar wind piles up here, compressed and heated, creating a chaotic environment. The heliosheath is roughly 40 to 50 astronomical units thick. Extending from the termination shock at about 84 astronomical units to the heliopause at about 120 to 130 astronomical units. Voyager 2 spent more than a decade crossing the heliosheath, measuring its properties. The region proved more complex than expected, with the solar wind's properties varying significantly depending on direction and solar activity. The plasma measurements showed that the solar wind in the heliosheath is not uniform. Sometimes the flow is smooth and steady, other times turbulent and gusty. The magnetic field twists and turns, sometimes aligning with the direction toward the Sun, sometimes pointing perpendicular to that direction. Scientists weren't sure what caused these variations. Some of the variability comes from changes in the Sun's output. The Sun goes through an 11-year activity cycle, alternating between periods of high activity with many sunspots and solar flares and periods of low activity with few sunspots. During high activity periods, the solar wind is stronger and more variable. During low activity periods, it's weaker and more steady. Voyager 2 crossed the heliosheath during both high and low activity periods, allowing scientists to study how solar activity affects the heliosheath. Some of the variability also comes from the structure of the heliosheath itself. Computer simulations suggest that the heliosheath is filled with structures called magnetic flux ropes, regions where the magnetic field lines are twisted into rope-like configurations. These structures can merge, split, and interact in complex ways, creating the turbulent environment Voyager 2 observed. The cosmic ray measurements in the heliosheath showed interesting behavior. As Voyager 2 moved farther from the termination shock toward the heliopause, the cosmic ray intensity continued to increase. But the increase wasn't smooth. There were periods where the intensity would suddenly drop, then recover, then drop again. These fluctuations were caused by transient events in the solar wind. When the sun produces a particularly strong burst of solar wind, it can temporarily push the heliopause farther out. This creates a region where cosmic rays are temporarily depleted. As the burst passes and the heliopause settles back to its normal position, the cosmic rays return. Voyager 2 measured several of these events during its traverse of the heliosheath, helping scientists understand how the sun's activity affects the boundary of the heliosphere. Then, on November 5, 2018, Voyager 2 crossed the heliopause. The crossing occurred at roughly 120 astronomical units from the Sun, about 11.1 billion miles. The plasma instruments detected a sudden change. The solar wind disappeared. In its place, the instruments measured the interstellar plasma, the thin gas that fills the space between stars. The transition was remarkably sharp. Within a few hours, the plasma density, temperature, and flow velocity all changed dramatically. The solar wind, which had been flowing outward from the Sun at roughly 250,000 miles per hour, simply stopped. The plasma Voyager 2 now measured was moving much more slowly, at only tens of thousands of miles per hour, and in a different direction. This was the interstellar plasma, gas that's part of the galaxy itself, not the Sun's outflow. The temperature dropped from nearly 1 million degrees in the heliosheath to roughly 60,000 degrees in the interstellar medium. The density changed as well, though in a complex way. The interstellar plasma is actually slightly denser than the solar wind in the outer heliosheath. This seems counterintuitive. You'd expect the interstellar medium to be less dense than the Sun's output. But the solar wind expands as it flows outward, spreading its particles over an ever larger volume. By the time it reaches the heliopause, it's become very thin. The interstellar medium, while incredibly tenuous by Earth standards, is actually slightly denser. Voyager 2 had entered interstellar space, the first spacecraft to do so with a working plasma instrument. Voyager 1 had crossed the heliopause 6 years earlier, in August 2012, but its plasma instrument had failed in 1980. Voyager 1's crossing was detected primarily through the cosmic ray detector and magnetometer. The cosmic ray intensity suddenly increased, and the magnetic field direction changed, indicating that the spacecraft had left the heliosphere. But without the plasma instrument, scientists couldn't directly measure the interstellar plasma properties. Voyager 2's working plasma instrument provided the first direct measurements of the interstellar plasma's properties. The data confirmed that the interstellar medium is denser and slightly warmer than the outer heliosphere. The measurements also revealed something unexpected about the magnetic field. Scientists had expected the interstellar magnetic field to be oriented in a particular direction based on observations of nearby stars and models of the galaxy's magnetic field. But Voyager 2's magnetometer showed that the field direction was different from predictions. The field was more tightly wound, more aligned with the heliopore's boundary than expected. This suggests that the interaction between the heliosphere and the interstellar medium is more complex than models predicted. The interstellar medium's magnetic field may be deflected or compressed by the expanding heliosphere, creating a layer of distorted field lines just beyond the heliopause. The cosmic ray measurements also provided insights. As expected, the cosmic ray intensity increased sharply at the heliopause. Cosmic rays from the galaxy could now reach the spacecraft without having to penetrate the heliosphere's magnetic barrier. But the increase wasn't uniform across all energies. Low-energy cosmic rays increased more than high-energy ones. This makes sense because low-energy particles are more easily deflected by magnetic fields. Inside the heliosphere, they can't penetrate at all. But high-energy cosmic rays can penetrate even the heliosphere's magnetic field, so their intensity doesn't change as much when crossing the heliopause. The data from the heliopause crossing has helped scientists refine their models of the heliosphere's structure. Before Voyager, the heliosphere was mostly theoretical. Scientists had models and predictions, but no direct measurements. Voyager 1 and 2 have now crossed the heliopause in 2 different locations, providing 2 data points about its properties. The crossings occurred at different distances from the Sun, 121 astronomical units for Voyager 1 and 120 for Voyager 2, and in different directions. This tells scientists that the heliopause is not perfectly spherical. Its distance from the Sun varies depending on direction, probably due to the Sun's motion through the interstellar medium and variations in the interstellar medium's density and pressure. The spacecraft is now traveling through true interstellar space. It's no longer in the Sun's protective bubble. The particles Voyager 2 now encounters come from interstellar space, from other stars, from supernova explosions, from the general background of the galaxy. This is the environment the spacecraft will travel through for the rest of its operational life and for tens of thousands of years beyond. The final place Voyager 2 will reach before it dies is right here, the local interstellar medium. Roughly 140 astronomical units from the Sun, about 13 billion miles from Earth. That's where the power will run out. That's where the signal will fade. That's where Voyager 2 will go dark. Not at some distant star, not at some dramatic boundary far ahead, but in the same region of space it already occupies right now. Still close to home on a galactic scale, still barely past the edge of the Sun's influence. The spacecraft will go silent here, long before it reaches anything else. And after that silence falls, it will continue drifting a dead object on an eternal trajectory toward things it will never be able to see or measure or report back on. Voyager 2 is heading in a specific direction through space. Relative to the Sun, it's moving at roughly 34,000 miles per hour. But the Sun itself is moving through the galaxy. The Sun orbits the galactic center once every 225 million years, moving at roughly 490,000 miles per hour. This means Voyager 2's motion through the galaxy is a combination of its motion relative to the Sun and the Sun's motion through the galaxy. The spacecraft is heading roughly toward the constellations of Sagittarius and Pavo in the southern celestial hemisphere. Its trajectory will carry it in that general direction for millennia. So, where does it go after it dies? What is it drifting toward across the tens of thousands of years that follow? Astronomers have calculated Voyager 2's trajectory and projected it forward, accounting for the gravitational influence of nearby stars. The calculations show that in roughly 40,000 years, Voyager 2 will pass within roughly 1.7 light-years of a star called Ross 248. Ross 248 is a small red dwarf star, one of the most common types of stars in the galaxy. Red dwarfs are small, cool stars with masses between about 8% and 50% of the Sun's mass. They burn their hydrogen fuel very slowly, giving them lifetimes measured in trillions of years. The Sun, by comparison, will exhaust its hydrogen fuel in about 5 billion years. Red dwarfs can burn for 10 trillion years or more, far longer than the current age of the universe. This incredible longevity comes from their low mass. Nuclear fusion in a star's core generates energy and pressure that holds the star up against gravity. Massive stars burn hot and bright, fusing hydrogen rapidly, but exhausting their fuel quickly. Low-mass red dwarfs burn cool and dim, fusing hydrogen slowly and lasting enormously long. Ross 248 has a mass of roughly 14% of the Sun's mass. It's much cooler and dimmer, with a surface temperature of roughly 5,400 degrees Fahrenheit compared to the Sun's 10,000 degrees. The star emits most of its light in the infrared part of the spectrum. If you could somehow stand near Ross 248 at the same distance Earth orbits from the Sun, the star would appear much dimmer and redder than the Sun. It would provide much less heat and light. A planet at Earth's orbital distance from Ross 248 would be frozen, far colder than Mars. For a planet to be warm enough for liquid water, it would need to orbit much closer to Ross 248, perhaps 10 to 20 times closer than Earth orbits the Sun. Such a close orbit would have strange consequences. The planet would likely become tidally locked, with one side always facing the star and the other side always facing away, just like the Moon is tidally locked to Earth. The star-facing side would be in perpetual daylight, potentially quite warm. The night side would be in perpetual darkness, frozen cold. Red dwarfs are also known for being active, producing powerful flares that can bathe nearby planets in radiation. Ross 248 is no exception. Observations have shown it produces flares that temporarily increase its brightness by significant amounts. Any planets in its habitable zone would be subjected to these intense bursts of radiation, making life as we know it unlikely unless organisms evolved strong radiation resistance. The star is so dim that despite being relatively close to Earth at roughly 10.3 light-years away, it's invisible to the naked eye. That's about 60 trillion miles. You need a telescope to see it. Its apparent magnitude is roughly 12.3, which is about 600 times fainter than the faintest stars visible to the naked eye under dark skies. Ross 248 is located in the constellation Andromeda. It's moving through space at a high velocity relative to most nearby stars. The star's velocity relative to the Sun is roughly 50 miles per second, or about 180,000 miles per hour. This high velocity is why Voyager 2 will encounter it. Both the spacecraft and the star happen to be moving through space in such a way that their paths will bring them relatively close together in about 40,000 years. The encounter will be completely passive. Voyager 2 will pass through Ross 248's outer system, far beyond any planets, if planets exist there. 1.7 light-years is roughly 10 trillion miles. For comparison, Neptune orbits the Sun at a distance of about 2.8 billion miles. Voyager 2 will pass Ross 248 at a distance roughly 3,600 times greater than Neptune's orbital distance. If Ross 248 has planets, they almost certainly orbit much closer than 1.7 light-years. Even the most distant objects in the Sun's system, comets in the Oort cloud, orbit at distances of roughly 1 light-year or less. So Voyager 2 won't come anywhere near Ross 248's planetary system. If it has one, the spacecraft will simply pass through the star's outer gravitational influence. At a distance of 1.7 light-years, Ross 248's gravity is incredibly weak. The star will have essentially no effect on Voyager 2's trajectory. The gravitational pull will be so small that it won't measurably change the spacecraft's speed or direction. Voyager 2 will sail past Ross 248, barely noticing the star's presence, continuing on its journey through the galaxy. If Ross 248 has planets with civilizations, and if those civilizations have telescopes capable of detecting small objects at interstellar distances, they might notice Voyager 2's passage. But that's an enormous if. Detecting an object the size of a car at a distance of 1.7 light-years would require extraordinary technology, far beyond anything we currently have. The spacecraft is small, dark, and emits no signals. It would be nearly impossible to detect unless you were specifically looking for it and knew exactly where to look. 1.7 light-years might not sound particularly close. That's roughly 10 trillion miles, or about 400 times the distance from the Sun to Neptune. But, in the context of interstellar space, it's a close approach. The average distance between stars in our region of the galaxy is roughly 4 to 5 light-years. So, Voyager 2 will pass Ross 248 at a distance roughly equal to half the average stellar separation. Of course, Voyager 2 won't be operational when it reaches Ross 248. The spacecraft's power supply will have been depleted decades earlier. Voyager 2 is powered by 3 radioisotope thermoelectric generators, or RTGs. These devices convert heat from the radioactive decay of plutonium-238 into electricity. The design is elegantly simple and remarkably reliable. Plutonium-238 is a radioactive isotope that decays by emitting alpha particles. Alpha particles are helium nuclei, each consisting of 2 protons and 2 neutrons. When an alpha particle is emitted, it carries away kinetic energy. This energy is converted to heat as the alpha particle collides with surrounding atoms. The RTG contains pellets of plutonium dioxide, a ceramic form of plutonium that's chemically stable and won't release the plutonium even if the RTG is damaged. The plutonium pellets are hot, reaching temperatures of roughly 1,200 degrees Fahrenheit. This heat flows outward through thermoelectric couples, devices made of 2 different semiconducting materials joined together. When one side of a thermoelectric couple is hot and the other side is cold, a voltage develops across the junction. Connect many thermoelectric couples in series, and you generate enough voltage to power the spacecraft. The cold side of the thermoelectric couples is connected to radiator fins that dissipate heat into space. The temperature difference between the hot plutonium pellets and the cold radiator fins drives the electricity generation. The efficiency is low, only about 6 to 7%. Most of the heat generated by the plutonium decay is wasted, radiated into space without being converted to electricity. But RTGs are incredibly reliable. They have no moving parts, nothing to wear out or break. As long as the plutonium is decaying, the RTG generates power. When the spacecraft launched, the RTGs produced roughly 470 watts of electricity, enough to power all of the spacecraft's systems with margin to spare. The spacecraft's instruments, computers, radio transmitter, and heaters all drew power from the RTGs. But plutonium-238 has a half-life of roughly 87.7 years. This means that every 87.7 years, the amount of plutonium decays to half of what it was. After 87.7 years, only half the original plutonium remains, producing only half the original heat. After another 87.7 years, only a quarter remains. The decay is exponential, following a predictable mathematical curve. As the plutonium decays, the RTGs produce less and less power. By the time Voyager 2 crossed the heliopause in 2018, the RTGs were producing roughly 250 watts, about half of their original output. The power output continues to decline by roughly 4 watts per year. This might not sound like much, but over decades, it adds up. Every year, the spacecraft has 4 watts less power to work with. Every decade, 40 watts less. Engineers have been managing this decline by shutting down systems that are no longer critical to the mission. Heaters have been turned off, allowing some parts of the spacecraft to drop to extremely cold temperatures. Parts of the spacecraft that were designed to operate at room temperature or slightly below are now operating at temperatures far below 0 Fahrenheit. This introduces risks. Materials become brittle when cold. Lubricants freeze. Electronic components can behave unpredictably. But the spacecraft has proven remarkably resilient. Systems that were never designed to operate at these temperatures continue functioning, a testament to the quality of the engineering and perhaps some good fortune. Non-essential instruments have been powered down. The imaging cameras were shut down after the Neptune encounter because there was nothing left to photograph. The ultraviolet and infrared spectrometers were turned off to save power. The photopolarimeter failed in 1991 and couldn't be restarted. The remaining operating instruments are the ones studying the space environment, the magnetometer, the cosmic ray subsystem, and the plasma wave subsystem. These instruments are still scientifically valuable because they're measuring the interstellar medium, something no other spacecraft has done. But even these instruments will eventually have to be shut down. The spacecraft's computer has been reprogrammed to use power more efficiently. Engineers have rewritten software to reduce the computer's processing load. They've adjusted the timing of data collection and transmission to minimize power consumption. They've turned off backup systems that are no longer needed. Every watt of power has been carefully managed, squeezed, optimized. Despite these efforts, the power available continues to decline. By 2026, Voyager 2 is already down to its last 3 instruments: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, which is itself scheduled for shutdown in 2026. The first instrument to be shut down will likely be one of the particle detectors. Then another. Then another. By the mid-2030s, the spacecraft likely won't have enough power to operate any instruments at all. The instruments will be turned off, one by one, each shutdown marking another step toward the mission's end. The last systems to be shut down will probably be the radio transmitter and receiver. As long as the spacecraft has enough power to run the radio, Engineers on Earth can still communicate with it, even if it can't collect any scientific data. The radio link is the spacecraft's last connection to Earth, the final thread tying it to the world that built it. But eventually, probably sometime in the late 2030s or early 2040s, the power output will drop below the minimum needed to run the radio. The transmitter requires roughly 23 watts to operate, plus power for the computer that formats the data and controls the transmission. When the RTGs can no longer provide that much power, the radio will go silent. The exact date depends on how well the RTGs continue performing and how efficiently engineers can manage the remaining power. It could be 2038. It could be 2042. It could be a few years earlier or later. But sometime in that decade, Voyager 2 will transmit its last signal. Engineers on Earth will receive the last bits of data, the last telemetry readings, the last status report, and then silence. At that point, Voyager 2 will go silent. The spacecraft will still exist, still traveling through interstellar space at 34,000 miles per hour. But it will be completely inert, unable to communicate, unable to collect data, unable to respond to commands from Earth. The instruments will be dark, their electronics cold and powerless. The computer will be frozen, its last program state preserved in non-volatile memory but unable to execute. The radio transmitter will be silent, its circuits unable to generate the signal that has linked the spacecraft to Earth for decades. It will become a derelict, a piece of human-made metal and electronics drifting through the galaxy. From that point forward, Voyager 2's fate will be determined entirely by the physics of orbital mechanics and the gravitational influence of nearby stars. It will continue on its trajectory, coasting through the vacuum of space with nothing to slow it down. In the vacuum of space, there's no air resistance, no friction, nothing to drain the spacecraft's momentum. It will continue moving at roughly 34,000 miles per hour, essentially forever, barring some extremely unlikely collision with an object. Collisions in interstellar space are extraordinarily unlikely. Space between the stars is incredibly empty. The interstellar medium contains roughly 1 atom per cubic centimeter on average. That's far more tenuous than the best vacuum we can create in laboratories on Earth. In comparison, the air you're breathing right now contains roughly 25 billion molecules per cubic centimeter. The interstellar medium is roughly 25 billion times less dense than the air around you. To put this emptiness in perspective, if you took all the matter in a cubic light year of interstellar space and compressed it to Earth's atmospheric density, it would fit in a volume smaller than a grape. The interstellar medium is essentially a perfect vacuum by any practical standard. This extreme emptiness means that Voyager 2 could travel for billions of years without hitting anything larger than a microscopic dust grain. The spacecraft is essentially traveling through nothing, through a void so empty that it's hard to even comprehend. Larger objects, asteroids, comets, rogue planets do exist in interstellar space, but they're incredibly rare and spread across vast distances. Asteroids and comets occasionally get ejected from planetary systems through gravitational interactions. A close encounter with a planet can accelerate an asteroid or comet to escape velocity, sending it out into interstellar space. Over billions of years, the galaxy has accumulated a population of these ejected objects. Some estimates suggest there could be trillions of rogue planets in the galaxy. Planets that were ejected from their birth systems and now drift through interstellar space without a parent star. But even with trillions of rogue planets, they're still incredibly rare when you consider the vast volume of the galaxy. The galaxy is roughly 100,000 light-years across and contains about 100 trillion cubic light-years of space. If there are a trillion rogue planets, that's only about 1 per 100 cubic light-years. The chance of Voyager 2 encountering one is vanishingly small. To understand how unlikely a collision is, consider that Voyager 2 is roughly 10 feet across and is traveling through space where the average distance to the nearest rogue planet might be several light-years. The spacecraft is a 10-foot target in a volume hundreds of trillions of miles across. The probability of hitting something is essentially zero. Even if Voyager 2 were to hit a small dust grain, the impact would be minor. Dust grains in interstellar space are typically microscopic, ranging from nanometers to micrometers in size. These are particles smaller than the width of a human hair. The spacecraft is moving at 34,000 miles per hour, which sounds fast, but on cosmic scales it's actually quite slow. Meteoroids hit Earth's atmosphere at speeds ranging from 25,000 to 160,000 miles per hour. When they hit, the friction with the atmosphere heats them to thousands of degrees, creating the bright streaks we call meteors. Voyager 2's speed is at the low end of this range. More importantly, there's no atmosphere in interstellar space to create friction. A dust grain hitting Voyager 2 would simply punch a tiny hole in whatever surface it hit. The impact would create a small crater, perhaps a fraction of a millimeter across. Over millions of years, the spacecraft might accumulate thousands or millions of these tiny impacts. The surface would become pitted and scarred. But the damage would be superficial. The spacecraft's structure wouldn't be compromised. Its electronics are protected inside the body of the spacecraft, shielded by aluminum and other materials. A microscopic dust grain isn't going to penetrate deep enough to damage critical systems. The spacecraft isn't moving fast enough to vaporize on impact with most small particles. It might accumulate a few pits or scratches on its surface over millions of years, but nothing catastrophic. So, barring some extraordinarily unlikely collision with a large object, Voyager 2 will simply continue drifting through space indefinitely. The interstellar medium itself is not completely uniform. While the average density is about 1 atom per cubic centimeter, there are regions where it's denser and regions where it's more tenuous. Dense clouds of gas and dust exist in some areas, regions where the density might be hundreds or thousands of atoms per cubic centimeter. These clouds are the birthplaces of stars. Over millions of years, gravity causes these clouds to collapse, forming new stars and planetary systems. If Voyager 2 were to pass through one of these dense clouds, it would experience a slightly higher rate of dust impacts. But even in a dense cloud, the environment is still essentially vacuum by Earth standards. A density of 1,000 atoms per cubic centimeter is still 25 billion times less dense than Earth's atmosphere. The spacecraft would barely notice the difference. There are also regions of extremely low density, called hot bubbles or superbubbles. These are cavities in the interstellar medium created by supernova explosions. When a massive star explodes as a supernova, it blasts away the surrounding gas, creating a bubble that can be hundreds of light-years across. The interior of these bubbles is filled with hot, tenuous gas at temperatures of millions of degrees, but at densities far below the average interstellar medium. If Voyager 2 passes through one of these bubbles, the cosmic ray detector might notice a change in the background radiation level. But otherwise, the spacecraft would be unaffected. The spacecraft is also exposed to radiation in interstellar space. Cosmic rays, high-energy particles from supernova explosions, and other energetic events constantly bombard the spacecraft. These particles can damage electronic components over time, gradually degrading their performance. This effect, called radiation damage, has been affecting Voyager 2 since launch. The spacecraft has accumulated radiation dose over decades of exposure. Some electronic components have degraded, their performance reduced by the cumulative damage. But the spacecraft was designed with radiation-hardened components that can tolerate high doses. The most critical systems use redundancy, with backup circuits that can take over if primary circuits fail. So far, the radiation damage hasn't caused any critical failures. The spacecraft continues operating despite decades of exposure to the harsh radiation environment of space. In interstellar space, the radiation environment is actually somewhat less harsh than in the solar system. The Sun produces its own radiation, including energetic particles from solar flares. Near Earth, we're protected by Earth's magnetic field, which deflects most of these particles. But in the outer solar system, spacecraft are exposed to solar radiation without protection. In interstellar space, the solar radiation is absent. The only radiation comes from galactic cosmic rays. These cosmic rays are more energetic, on average, than solar radiation, but the flux is lower. So the overall radiation dose rate might actually be slightly lower in interstellar space than in the outer solar system. So barring some extraordinarily unlikely collision, Voyager 2 will simply continue drifting through space indefinitely. It will pass Ross 248 in roughly 40,000 years. After that, it will continue on, eventually passing other stars over hundreds of thousands and millions of years. Astronomers have calculated that in roughly 296,000 years, Voyager 2 will pass within roughly 4.3 light-years of Sirius. Sirius is the brightest star in Earth's night sky, a blue-white star roughly twice the mass of the Sun, located about 8.6 light-years from Earth. Sirius is actually a binary star system. The bright star we see, called Sirius A, is orbited by a faint white dwarf companion called Sirius B. Sirius A is a main sequence star, burning hydrogen in its core just like the Sun, but it's much hotter and more luminous. Its surface temperature is roughly 18,000 degrees Fahrenheit compared to the Sun's 10,000 degrees. It emits roughly 25 times more energy than the Sun. If the Sun were replaced by Sirius A, Earth would receive 25 times more heat and light. The oceans would boil. The atmosphere would be stripped away. Earth would be completely uninhabitable. Sirius B is a white dwarf, the remnant core of a star that exhausted its nuclear fuel. White dwarfs are incredibly dense. Sirius B has roughly the mass of the Sun compressed into a sphere about the size of Earth. A teaspoon of white dwarf material would weigh several tons on Earth. The star is so dense that its gravity is immense. If you could somehow stand on its surface, you'd weigh hundreds of thousands of times more than on Earth. Sirius B shines not through nuclear fusion, but through residual heat left over from when it was a normal star. It's slowly cooling, radiating its stored heat into space. Over billions of years, it will cool to the point where it no longer emits visible light. At that point, it will be called a black dwarf, though the universe isn't old enough for any black dwarfs to exist yet. The two stars orbit each other every 50 years. Their orbits bring them as close as 8 astronomical units, about the distance from the Sun to Saturn, and as far as 31 astronomical units, about the distance from the Sun to Neptune. When Voyager 2 passes Sirius in 296,000 years, both stars will still be shining. Sirius A will still be a bright blue-white star, though it will have aged slightly. Sirius B will still be a white dwarf, slightly cooler than it is today, but still hot enough to emit visible light. 4.3 light-years is roughly the distance from the Sun to Proxima Centauri, the nearest star to our solar system. So Voyager 2 will pass Sirius at a distance comparable to the nearest neighboring star. At that distance, Sirius will have essentially no effect on Voyager 2's trajectory. The gravitational pull will be negligible. Again, the spacecraft will be long dead by then, drifting silently through the darkness. Its power supply will have been exhausted for more than 250,000 years. The spacecraft will be cold, frozen to the temperature of interstellar space, roughly minus 450 degrees Fahrenheit. The encounter with Sirius will be entirely passive. The spacecraft will pass through Sirius's gravitational influence, and its trajectory will be slightly altered, bent by the star's gravity. But the change will be minor, and Voyager 2 will continue on. The deflection will be so small that it would be difficult to measure, even if we had instruments tracking the spacecraft. The gravitational influence of a star at a distance of 4.3 light-years is incredibly weak. It's enough to slightly curve the spacecraft's path, but not enough to capture it into orbit or significantly change its speed. Beyond Sirius, Voyager 2's future encounters become more uncertain. The spacecraft will undoubtedly pass near other stars over the next millions of years. But predicting exactly which stars it will encounter and when becomes increasingly difficult. The problem is that stars are also moving. They orbit the galactic center just like the Sun does, but each on its own path. Some stars move quickly relative to the Sun, others slowly. Some are moving toward us, others away. Over thousands of years, these stellar motions change the positions of stars relative to each other. A star that's currently far from Voyager 2's path might move into its path over the next 100,000 years. A star that's currently close might move away. Calculating Voyager 2's trajectory 1,000,000 years into the future requires knowing the positions and velocities of hundreds of nearby stars. Even small uncertainties in those positions and velocities accumulate over time, making the long-term trajectory increasingly uncertain. Astronomers can say, with reasonable confidence, where Voyager 2 will be in 50,000 or 100,000 years. But predicting where it will be 1,000,000 years from now involves significant uncertainty. And predicting where it will be 10 million years from now is little better than guessing. The spacecraft's trajectory becomes chaotic in the mathematical sense. Small changes in initial conditions lead to large differences in outcomes over time. This doesn't mean the spacecraft's motion is random. It's still governed by Newton's laws of motion and gravity. But it does mean that long-term predictions become unreliable. Despite this uncertainty, we can make some general statements about Voyager 2's future. Over millions of years, Voyager 2 will have many such encounters with stars. Each encounter will slightly alter the spacecraft's trajectory, bending its path this way or that. Some encounters will speed the spacecraft up slightly, others will slow it down. Some will deflect it to the left, others to the right. Over time, these small changes will accumulate, making the spacecraft's long-term trajectory increasingly uncertain. The cumulative effect of many small gravitational perturbations becomes significant. This is similar to how the motion of planets in the solar system becomes chaotic over very long timescales. We can predict where Earth will be next year with extraordinary precision. We can predict where it will be in 1,000 years with good accuracy. But predicting where Earth will be 100 million years from now is much harder. Small uncertainties in the current orbital parameters, combined with gravitational perturbations from other planets, make the long-term behavior unpredictable. Voyager 2's motion through the galaxy faces the same challenges. Predicting where Voyager 2 will be 1,000,000 years from now is relatively straightforward. You calculate its current trajectory, account for the gravitational influence of nearby stars, and project forward. Predicting where it will be 10 million years from now is much harder. Predicting where it will be 1 billion years from now is essentially impossible. The trajectory becomes chaotic, sensitively dependent on tiny uncertainties in the positions and velocities of nearby stars. But we can say with confidence that Voyager 2 will continue orbiting the galaxy along with the Sun and all the other stars in our region of the Milky Way. The spacecraft is gravitationally bound to the galaxy. It's not moving fast enough to escape the galaxy's gravitational pull. So it will remain in the Milky Way, orbiting the galactic center just like the Sun does, but on a different trajectory. Over hundreds of millions of years, Voyager 2 will complete its own orbit around the galactic center. The Sun orbits the galactic center once every 225 million years. Voyager 2, moving on a different path, will have a different orbital period, but it will be in the same general range. Both the spacecraft and the Sun are essentially just objects in orbit around the galaxy's center, held in place by the combined gravitational pull of all the stars, gas, and dark matter in the galaxy. What will finally end Voyager 2's journey? Not a collision, probably. Not running out of momentum, because in the vacuum of space, there's nothing to slow it down. The answer is that Voyager 2 will likely continue drifting through the galaxy for billions of years until the galaxy itself changes so much that the concept of the spacecraft's trajectory becomes meaningless. In roughly 4 billion years, the Milky Way will collide with the Andromeda galaxy. The two galaxies will merge over the course of several billion years, creating a new, larger galaxy. During this merger, stars will be scattered, their orbits randomized by the gravitational chaos of the collision. Voyager 2 will be caught up in this chaos, its trajectory altered by the gravitational influence of passing stars and the overall restructuring of the galaxy. The spacecraft will likely survive the merger physically. The distances between stars are so vast that actual collisions between stars are rare even during galaxy mergers. But the spacecraft's orbit will be completely scrambled, sent into some new trajectory in the merged galaxy. Beyond that, we're talking about timescales so long that other processes start to matter. Over trillions of years, stars will exhaust their fuel and fade. The Sun will become a white dwarf, then gradually cool to a black dwarf over tens of billions of years. Other stars will do the same. Eventually, the galaxy will be filled mostly with dead stellar remnants, white dwarfs, neutron stars, black holes, and the occasional long-lived red dwarf still burning its fuel. Voyager 2 will drift among these dead stars, a silent artifact from a civilization that existed trillions of years earlier. On even longer timescales, roughly 100 billion years from now, stellar orbits will decay through a process called gravitational radiation. Any object in orbit emits gravitational waves, ripples in space-time that carry away energy. For normal objects orbiting at normal speeds, this energy loss is utterly negligible. But over timescales of 100 billion years, it adds up. Stars, planets, and spacecraft in orbit around the galactic center will gradually spiral inward, their orbits decaying as they lose energy to gravitational radiation. Voyager 2 will eventually spiral into the galactic center along with everything else. But 100 billion years is such an incomprehensibly long time that it's hard to even describe. It's a 1 followed by 20 zeros. 100 billion years. The universe is currently about 13.8 billion years old. 100 billion years is roughly 7 billion times the current age of the universe. To put this in perspective, imagine the entire history of the universe from the Big Bang to now compressed into a single second. On that scale, 10 to the 20th years would be more than 200 years. These timescales are so far beyond human comprehension that they're almost meaningless. But they give us a sense of just how long Voyager 2 could potentially exist. Barring some unlikely collision or disintegration from micrometeorite impacts, the spacecraft could drift through the galaxy for trillions upon trillions of years. Long after Earth is gone. Long after the Sun is dead. Long after humanity, if it still exists, has evolved into something completely unrecognizable or spread across the galaxy or gone extinct. Voyager 2 will still be out there, a tiny piece of metal and electronics carrying a golden record with sounds and images from a planet that no longer exists. The golden record is one of the most famous aspects of the Voyager missions. Each Voyager spacecraft carries a 12-inch gold-plated copper disc containing sounds and images selected to represent the diversity of life and culture on Earth. The project was led by a committee chaired by Carl Sagan, the astronomer and science communicator who would later become famous for the Cosmos television series. Sagan and his team had an impossible task. How do you represent all of Earth, all of humanity, all of our history and culture on a single record? What do you include? What do you leave out? How do you explain who we are to someone who might be utterly different from us, with different senses, different ways of thinking, different concepts of reality? The team decided to include a variety of content, trying to cover as many aspects of Earth and human civilization as possible. The record includes greetings in 55 languages, from ancient Sumerian and Hittite to modern Mandarin, English, and Swahili. Each greeting is brief, just a few sentences, but together they represent the linguistic diversity of humanity. Some greetings are formal, others casual. Some express hope for peace, others simply say hello. The record includes sounds from nature: thunder rumbling, wind blowing, rain falling, surf crashing on a beach, a waterfall, a stream, birds singing, whales calling, elephants trumpeting. These sounds were meant to convey the richness of Earth's natural environment, the diversity of life and ecosystems. It includes sounds of human activity: footsteps, heartbeats, laughter, a baby crying, a kiss, a mother's first words to her newborn child, tools being used, a saw cutting wood, a hammer striking metal, vehicles, a horse and cart, a train, a car, an airplane taking off. These sounds were meant to show how humans interact with their environment, how we use tools, how we travel. The record includes music from various cultures and time periods. Bach, Beethoven, Mozart, representing Western classical music. Chuck Berry's Johnny B. Good, representing rock and roll. Traditional music from Java, Peru, Zaire, India, Japan, and other cultures. The selection was meant to show the diversity of human musical expression, though, inevitably, it was limited by what could fit on one record. Each piece of music was chosen to represent a different aspect of human creativity, different emotions, different cultural traditions. The record includes 116 images showing scenes from Earth, mathematical and physical constants to provide a universal reference frame, diagrams of DNA structure, cell division, human anatomy, images of landscapes, mountains, oceans, deserts, forests, images of animals, insects, fish, birds, reptiles, mammals, images of humans from various cultures, showing different activities, different ages, different settings, images of architecture, from ancient structures to modern cities, images of technology, scientific instruments, spacecraft. The images were encoded as analog signals. Each image was converted into a waveform that could be etched into the grooves of the record. To decode the images, you'd need to understand the encoding scheme. Instructions for doing so are etched onto the jacket of the record. The instructions use symbolic language, trying to be as universal as possible. They show the basic principles of the encoding, the scan rate, the number of lines per image. They assume the finder has some understanding of mathematics and physics, but try not to assume too much about their specific knowledge or capabilities. The record is encased in a protective aluminum jacket, along with a cartridge and a needle for playing it. The jacket is designed to protect the record from radiation, micrometeorite impacts, and the extreme temperature variations of space. The record itself is gold-plated to prevent corrosion. Gold is chemically inert and won't oxidize or corrode even over billions of years. The images and sounds are encoded as analog waveforms, etched into the grooves of the record, just like a vinyl LP. As long as the physical structure of the record remains intact, the information can theoretically be recovered. The record also includes a sample of uranium-238 in its pure form. This was included as a kind of radioactive clock. Uranium-238 has a half-life of 4.5 billion years. By measuring how much of the uranium has decayed into lead, someone finding the record could determine how long ago it was created. This would tell them roughly when the Voyager mission took place, even if they couldn't decode any of the other information on the record. The record was designed to last for billions of years in the space environment. The materials were chosen for their durability. The gold plating won't corrode. The copper substrate won't degrade in the vacuum of space. The aluminum jacket will protect the record from most hazards. Barring a direct collision with something large enough to destroy it, the record should remain intact, essentially indefinitely. The information encoded on it could theoretically be recovered billions of years from now. Of course, the chance of any extraterrestrial civilization actually finding Voyager 2 and recovering the record is essentially zero. Space is too big. The spacecraft is too small. The galaxy contains hundreds of billions of stars, most with planetary systems. If intelligent civilizations exist on even a tiny fraction of those planets, there could be thousands or millions of civilizations in the galaxy. But they're spread across hundreds of thousands of light years. The chance of one of them happening to be in the right place at the right time to detect Voyager 2 as it passes through their stellar neighborhood is vanishingly small. Even if an advanced civilization existed somewhere in the galaxy and was actively searching for artifacts from other civilizations, the probability of them finding this one tiny object drifting through the void is astronomically low. They'd need to be scanning their local stellar neighborhood with instruments sensitive enough to detect objects the size of a car at distances of light years. They'd need to happen to be looking in the right direction at the right time. They'd need to send a probe to investigate when they detected something. And they'd need to do all of this within the window of time when Voyager 2 happens to be passing through their region of space. The odds against all of these things lining up are enormous. The Golden Record was never really about communication with aliens. It was about the statement it made to ourselves. It was about the idea that humanity could create something that might outlast our civilization, our planet, our sun. It was a message in a bottle cast into the cosmic ocean, not with any real expectation of it being found, but as an expression of hope and curiosity and the human desire to reach beyond our limits. Carl Sagan, who led the team that created the Golden Record, described it as a symbol of optimism about humanity's future. At a time when the Cold War threatened nuclear annihilation, when the future looked uncertain, the Golden Record represented the idea that humanity might endure, might reach the stars, might leave some mark on the universe. It was a statement that we existed, that we created art and music and science, that we wondered about the cosmos and our place in it. The record was as much for us as for any hypothetical alien finder. It was a time capsule, a snapshot of Earth and humanity in 1977. It captured a moment in our history, a particular set of choices about what we thought was important, what we thought represented us. Future generations looking back at the Golden Record can see what we valued, what we chose to include, what we thought would best represent humanity to the cosmos. In that sense, the Golden Record is a kind of mirror. It shows us ourselves, our hopes and dreams, our creativity and curiosity, our desire to connect with something beyond ourselves. It's a reminder that we're part of something larger, part of a universe filled with wonders and mysteries, and that we have the capacity to reach out, to explore, to create things that might outlast us. Voyager 2's true final destination isn't Ross, 2, 4, 8, or Sirius, or any other specific star. Its final destination is the far future. The spacecraft will drift through the galaxy for billions of years, long after the civilization that built it has disappeared. It will outlast the Earth, which will be sterilized by the sun's increasing luminosity in roughly 1 billion years, and eventually consumed when the sun expands into a red giant in about 5 billion years. It will outlast the sun itself, which will shed its outer layers and fade to a white dwarf, then gradually cool over tens of billions of years. It will witness the collision and merger of the Milky Way and Andromeda galaxies, its trajectory scrambled by the gravitational chaos of that event. It will drift among the stars as they age and die, as the galaxy gradually goes dark, as star formation ceases and the last stars burn out. The Voyager missions transformed our understanding of the outer planets. Before Voyager, Jupiter, Saturn, Uranus, and Neptune were just points of light in telescopes. We knew they were giant planets. We knew they had moons. We knew some had rings. But we didn't really understand them. We didn't know what their atmospheres looked like up close, what their moons were like, what their magnetic environments were like. Voyager changed all of that. The images from Jupiter revealed a world of incredible complexity. The Great Red Spot, a storm larger than Earth that's been raging for centuries. The turbulent cloud bands driven by winds hundreds of miles per hour. The volcanic eruptions on Io, the first active volcanism discovered beyond Earth. The smooth ice surface of Europa, hinting at an ocean beneath that might harbor life. The ancient cratered surfaces of Ganymede and Callisto, recording billions of years of impacts. These discoveries fundamentally changed how we think about the solar system. Before Voyager, most scientists thought moons were dead, inert bodies. Voyager showed that some moons are geologically active, with volcanism, tectonics, possibly even subsurface oceans. The Saturn encounter revealed the intricate structure of the rings in detail never before seen. Thousands of individual ringlets separated by gaps. Waves and kinks in the rings, caused by the gravitational influence of moons. The shepherd moons that keep some rings confined. The discoveries about Saturn's atmosphere and magnetic field. All of this was new, expanding our knowledge dramatically. Uranus was particularly surprising. The extreme tilt of its rotation axis, 98 degrees, meaning it essentially rolls on its side as it orbits the Sun. The strange tilted magnetic field, offset from the planet's center. The 10 new moons discovered, adding to the 5 previously known. The faint rings, barely detectable, but definitely there. Neptune showed us that even far from the Sun, a planet can be dynamic and active. The Great Dark Spot, a storm system that has since disappeared, showing that Neptune's atmosphere is constantly changing. The incredibly fast winds, the fastest in the solar system. The active geysers on Triton, making it one of the few geologically active bodies in the outer solar system. All of these discoveries came from Voyager. All of this knowledge that we now take for granted, that's in textbooks and documentaries, came from these 2 spacecraft in the late 1970s and 1980s. The missions also demonstrated what's possible with careful planning, ingenious engineering, and dedicated teamwork. The Grand Tour alignment of the outer planets was recognized in the 1960s. NASA engineers calculated that a spacecraft launched in 1977 could visit all 4 outer planets using gravitational assists. But the mission was ambitious, perhaps too ambitious. The spacecraft would have to operate for at least 12 years to reach Neptune. That was far longer than any spacecraft had operated before. The spacecraft would have to survive the harsh radiation environment of Jupiter. It would have to navigate precisely from planet to planet using gravitational assists. It would have to operate autonomously, making decisions without waiting for instructions from Earth. Many people doubted it could be done. But the engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, were determined to try. They designed a spacecraft that was robust, reliable, and capable. They built in redundancy, so that if one system failed, a backup could take over. They tested everything extensively, subjecting the spacecraft to radiation, vibration, thermal cycling, vacuum. They planned every detail of the encounters, calculating trajectories, timing, instrument observations, programming sequences months in advance. And it worked. Not perfectly, There were problems and failures along the way, but the mission succeeded beyond anyone's expectations. Both Voyager spacecraft completed the Grand Tour. Both are still operating nearly 50 years later. The missions inspired a generation of scientists and engineers. People who saw the first images of Jupiter's moons or Saturn's rings and decided they wanted to work in space exploration. People who are now leading missions to Europa, Titan, and other worlds that Voyager first revealed as interesting destinations. The Voyager missions showed that exploration is possible, that we can send our instruments to distant worlds and learn about them, that the solar system is accessible if we're willing to make the effort. This inspiration continues today. New missions to the outer planets build on what Voyager discovered. The Galileo mission, which orbited Jupiter from 1995 to 2003, followed up on Voyager's discoveries. The Cassini mission, which orbited Saturn from 2004 to 2017, spent 13 years studying the Saturn system in detail. The Juno mission, currently orbiting Jupiter, is studying the planet's interior structure and magnetic field. The Europa Clipper mission, which launched in 2024, will study Europa's subsurface ocean in detail. All of these missions owe a debt to Voyager. Voyager showed us these worlds were worth studying. Voyager gave us the first detailed look at what was there. Voyager inspired the next generation of explorers. The Voyager missions also demonstrated humanity's ability to think beyond immediate concerns. In 1977, the world was dealing with economic recession, political turmoil, social unrest. The Cold War was ongoing. The energy crisis was affecting economies worldwide. Many people questioned whether space exploration was worth the cost. Yet NASA proceeded with Voyager. The missions weren't solving any immediate problems on Earth. They weren't curing diseases or feeding hungry people or ending conflicts. They were pure exploration, driven by curiosity and the desire to understand. And yet they were funded, launched, completed. This reflects something important about humanity. We're capable of looking beyond our immediate needs and problems. We're capable of investing in long-term endeavors that may not have immediate payoffs. We're capable of doing things simply because they're worth doing, because they expand our knowledge and capabilities. The Voyager missions are examples of this. They represent humanity at its best, curious, ambitious, collaborative, thinking beyond the present toward the future. The Golden Record embodies this spirit. It wasn't necessary for the mission's scientific objectives. The spacecraft would have functioned exactly the same without it. But it was included anyway, as a message to the future, as a symbol of hope and possibility. The record says something important about who we are and what we value. It says we create art and music. We speak many languages and live in many different cultures. We share one planet, one home, despite our differences. We wonder about the cosmos and our place in it. We hope that our civilization will endure, will reach the stars, will make contact with others who might be out there. These are not practical considerations. They're philosophical, almost spiritual, but they're part of why we explore. Not just to gather data and publish papers, but to satisfy a deeper need to understand, to connect, to reach beyond ourselves. Voyager carries this spirit with it. The spacecraft is a physical embodiment of human curiosity and ambition. Every component, every line of code, every decision made by the mission team represents countless hours of human effort and ingenuity. The scientists who proposed the mission, the engineers who designed the spacecraft, the technicians who built and tested it, the mission controllers who guided it through the planetary encounters, the mathematicians who calculated the trajectories, the programmers who wrote the software, the administrators who secured the funding. All of these people contributed to making Voyager possible, and their work will endure. Long after they're gone, long after their names are forgotten, Voyager will still be traveling through the galaxy, carrying the result of their efforts. This is perhaps the most profound aspect of the mission. We create things that outlast us. We leave marks on the universe that persist long after we're gone. Voyager is one of those marks, a permanent addition to the galaxy's inventory of objects. A piece of Earth, wandering the cosmos forever. Eventually, on timescales so long that numbers lose meaning, the spacecraft's orbit will decay, and it will spiral into whatever remains of the galactic center. Or perhaps it will be captured by a star's gravity and drawn into orbit around some stellar remnant. Or perhaps it will collide with something, vaporized in an impact after trillions of years of near misses. We don't know exactly what will happen to Voyager 2 in the far future, but we know it will continue existing long after we're gone. The spacecraft is currently about 13 billion miles from Earth, traveling at 34,000 miles per hour. Every second, it moves another 9.4 miles farther away. Every hour, another 34,000 miles. Every day, another 816,000 miles. The distance grows relentlessly, steadily, irreversibly. As of now, in 2026, Voyager 2 is still operational. The instruments are still collecting data about the interstellar medium. The magnetometer is still measuring the magnetic field. The plasma wave subsystem is still detecting radio emissions and plasma waves. The cosmic ray subsystem is still counting high-energy particles, though it is scheduled to be powered down in 2026. All of this data is transmitted back to Earth, received by the Deep Space Network, processed by mission scientists, and published in scientific journals. Even now, nearly 50 years after launch, Voyager 2 is still making discoveries, still contributing to our understanding of the universe. Recent data has revealed that the interstellar magnetic field is stronger than expected. The boundary between the heliosphere and interstellar space is more complex than models predicted. The cosmic ray environment changes on timescales of months to years, possibly due to variations in the local interstellar medium or changes in solar activity affecting the heliosphere's size. These findings are helping scientists refine their understanding of how the heliosphere interacts with the interstellar medium. But the mission is winding down. Each year, the power available decreases by roughly 4 watts. Each year, engineers have to make difficult decisions about which systems to turn off to conserve power. In recent years, heaters have been turned off to save power. Parts of the spacecraft that were designed to operate at moderate temperatures are now operating far below 0 Fahrenheit. This creates risks. Materials become brittle when cold, lubricants freeze, electronic components behave unpredictably. But the spacecraft has proven remarkably resilient, continuing to operate despite conditions far outside its design parameters. Engineers have also reprogrammed the spacecraft's computer to optimize power usage. They've rewritten software routines to be more efficient. They've adjusted data collection schedules to minimize power consumption. They've turned off backup systems that are no longer needed. Every watt has been carefully managed, every system optimized, every decision made with the goal of keeping the mission running as long as possible. But there's only so much that can be done. The power output from the RTGs continues to decline, following the inevitable decay of plutonium-238. No amount of clever engineering can change that fundamental physics. Current projections suggest that sometime in the late 2020s, probably around 2028 or 2029, the spacecraft will no longer have enough power to operate any scientific instruments. The instruments will be shut down one by one. Perhaps the cosmic ray detector will go first. Then the low-energy charged particle detector. Then the magnetometer. Then finally, the plasma instrument, the most important instrument for studying the interstellar medium. After that, the spacecraft will continue operating, but without collecting any science data. The only systems still running will be the computer, the radio transmitter and receiver, and perhaps some minimal spacecraft control systems. This phase might last several more years. As long as the spacecraft can transmit a signal, as long as engineers on Earth can receive telemetry, the mission continues in some form. Engineers will monitor the spacecraft's health, tracking temperature, power levels, system status. They'll send occasional commands, adjusting pointing, testing systems, optimizing what little functionality remains. But eventually, probably in the late 2030s or early 2040s, the power will drop below the minimum needed to run the radio. When that happens, Voyager 2 will transmit its final signal. Some engineer at the Deep Space Network will receive the last packet of data. They'll see the telemetry readings, the power level, the temperature, the status of various systems, and then silence. No more signals. No more data. No more communication. The mission will be over. There will probably be a press release from NASA announcing the end of communication with Voyager 2. There will probably be news articles remembering the mission's achievements. Scientists who worked on the mission will be interviewed. Images from the planetary encounters will be shown again. The golden record will be mentioned. People will reflect on what the mission meant, what it accomplished, what it represented, and then Voyager 2 will fade from public consciousness. It will become history, another achievement from the past. Young people will learn about it in school, the same way they learn about the Apollo moon landings or the Viking Mars landers. It will be part of the story of space exploration, one chapter in a larger narrative. But the spacecraft itself will continue. Silent and dark, yes. Unable to communicate, unable to observe, unable to respond. But still there, still moving, still traveling through space at 34,000 miles per hour. Still carrying its instruments, though unpowered. Still carrying its golden record, though unplayed. Still carrying the marks and signatures of the people who built it, though those people are long gone. The spacecraft will become a time capsule, preserving a moment from 1977. The state of technology at that time. The hopes and aspirations of that era. The music and images chosen to represent Earth, all of it frozen, preserved, carried forward into the future by a machine that will outlast everything that created it. We can still communicate with Voyager 2, but that window is closing. In another decade or two, the spacecraft will go silent, its power supply finally exhausted. From that point on, It will be beyond our reach, traveling through a universe we can observe but not touch. The Voyager missions were initially planned to last 5 years, just long enough to reach Jupiter and Saturn. Voyager 2 has now been operating for nearly 50 years, 10 times longer than planned. It's a testament to the quality of the engineering, the dedication of the mission team, and perhaps a bit of luck. When Voyager 2 finally goes silent, when the last bit of data is received and the signal fades into noise, it will mark the end of an era, the end of humanity's first missions to the outer planets, the end of our first ventures into interstellar space. But the spacecraft itself will continue. Silent and alone, yes, but still traveling, still carrying its golden record, still representing humanity's first tentative steps beyond our solar system. In 40,000 years, it will pass Ross 248. If any observers exist in that star system, they won't see Voyager 2. The spacecraft is too small, too far away, too dark. It reflects no light, emits no signals, leaves no trail. It will pass through Ross 248's outer system, completely undetected, a ghost ship from a distant world. In 296,000 years, it will pass Sirius, again unseen and unknown. Over millions and billions of years, it will continue its journey, a silent witness to the evolution and eventual death of the galaxy. The spacecraft will exist in a future so remote that we can barely imagine it. A future where Earth might be gone, where the sun might be cold, where humanity might be extinct or transformed into something we wouldn't recognize. But Voyager 2 will still be there, drifting through the dark, carrying its message from a vanished world. There's something both profound and melancholy about Voyager 2's journey. Profound, because this tiny machine represents humanity's ability to create something that transcends our own existence. We are temporary. Our civilizations rise and fall. Our planet will eventually become uninhabitable. Our sun will die. But Voyager 2 will endure, carrying evidence that we existed, that we wondered about the universe, that we tried to reach beyond our limits. Melancholy, because the spacecraft's future is one of eternal isolation. It will never return to Earth. It will never be recovered or studied or placed in a museum. It will drift alone through the galaxy for billions of years, with no one to observe it, no one to remember it, no one to know its story. Unless, of course, it is found. The odds are astronomically small, but not zero. Perhaps somewhere in the galaxy, a civilization exists that has the technology to detect small objects drifting through interstellar space. Perhaps they scan their stellar neighborhood, cataloging everything that moves through it. Perhaps they detect Voyager 2's passage through their system and send a probe to investigate. Perhaps they recover the golden record and decode its contents. Perhaps they see the images of Earth, hear the sounds, listen to the greetings, and wonder about the civilization that created this artifact. Perhaps they marvel at the audacity of a species that would send a message to the stars, knowing it might never be received. Or perhaps not. Perhaps Voyager 2 will drift through the galaxy forever, its message unread, its journey unobserved, its fate unknown. Either way, the spacecraft will continue. It exists now in interstellar space, farther from home than any human-made object has ever traveled. It will pass Ross 248 in 40,000 years, moving at 34,000 miles per hour through the dark, long after it has gone silent. That silent drift through the galaxy is what follows. not a destination. A journey without a traveler, the body still moving long after the mission has ended. Voyager 2's journey is ongoing. It has been traveling for nearly 50 years and will continue traveling for billions more. We built it, launched it, guided it through the outer solar system, and watched it cross into interstellar space. Now, it's beyond our control, beyond our reach, embarked on a voyage that will outlast everything we know. In another decade or two, we'll lose contact. The spacecraft will go silent, its power supply exhausted, its transmitter dead. From that moment on, Voyager 2 will be truly alone, traveling through a darkness so complete that even the light of the sun will be just another star in the sky. And yet, it will continue, moving at 34,000 miles per hour, covering a light year every 18,000 years, passing Ross 248 in 40,000 years, passing Sirius in 296,000 years, orbiting the galaxy alongside the sun and the stars, drifting through the future, a silent ambassador from Earth. The engineers who designed Voyager 2 are mostly retired now or gone. The scientists who analyzed its data from Jupiter and Saturn and Uranus and Neptune have moved on to other projects or ended their careers. The younger generation of mission controllers who manage the crossing of the heliopause will themselves retire in the coming decades. Eventually, no one alive will remember the launch, the planetary encounters, the excitement of discovery. Voyager 2 will become history, then legend, then perhaps forgotten entirely. But the spacecraft will still be out there. Long after the last person who remembers it has passed away, long after the mission is forgotten, the spacecraft will continue its journey. It's a strange thought. We create these machines, send them into space, and then they outlive us. They outlive our civilization. They become permanent parts of the universe, artifacts that will exist long after their creators are dust. Voyager 2 is humanity's most distant representative. It's the farthest object we've sent from Earth that's still sending back data. Soon it will go silent, but it will remain our most distant creation, drifting farther and farther away with every passing second. Right now, at this very moment, Voyager 2 is about 13 billion miles from Earth. By the time you finish reading this sentence, it will be another 100 miles farther away. By tomorrow, another 816,000 miles. By next year, another 298 million miles. The numbers are so large, they become abstract, meaningless. We can write them down, but we can't really grasp them. 13 billion miles. 40,000 years to the nearest star on its path. Billions of years of existence ahead of it. These scales exceed our intuition, our ability to visualize, our capacity to comprehend. But they're real. Voyager 2 is out there right now, moving through the dark, carrying its golden record, traveling toward a future we cannot imagine. What does it mean that we sent Voyager 2 into space? What does it say about us as a species? It says we're curious. We wanted to see the outer planets up close, to understand them, to study their atmospheres and moons and rings. It says we're ambitious. We designed and built a spacecraft that could survive the harsh environment of space for decades, that could navigate from planet to planet with incredible precision, that could send data across billions of miles. It says we think about the future. We included the golden record, knowing that Voyager 2 would outlast our civilization, that it might be the only evidence of our existence that survives into the far future. It says we're willing to invest resources in endeavors that have no immediate practical benefit. Voyager 2 didn't solve any pressing problems on Earth. It didn't cure diseases, or end poverty, or prevent wars. It was pure exploration, pure science, driven by curiosity and the desire to understand. And it says we're optimistic, at least sometimes. We sent a message to the stars, believing that the future might be better than the present, that humanity might survive, that someone, someday, somewhere, might find our message and know that we existed. Voyager 2's trajectory is set. Its future course is determined by the laws of physics, by the gravitational pull of nearby stars, by the motion of the galaxy. We can calculate where it will be thousands or millions of years from now, at least approximately. But, in a deeper sense, Voyager 2's future is unknown. We don't know what the galaxy will be like in 1 billion years. We don't know if any civilizations will exist, if anyone will be watching, if anyone will care about a small metal object drifting through the dark. We don't know if the universe itself will endure, if the laws of physics will remain constant, if the stars will keep burning or gradually fade. All we know is that Voyager 2 exists now, that it's traveling through interstellar space, that it will continue traveling for billions of years. It's a tiny object in a vast universe, but it's ours. We built it. We sent it on its journey. And in some small way, it represents us, our curiosity, our ambition, our hope. The final place Voyager 2 will reach before it dies is the local interstellar medium. Not a star. Not a boundary far ahead. Not Ross 248, which is 40,000 years away, and which Voyager 2 will reach only as a dead, silent object. The answer is here. The place where it is right now. Roughly 140 astronomical units from the Sun, drifting through the thin plasma between the stars, still measuring, still transmitting, still connected to Earth by a thread of radio signal that grows fainter every year. That connection will break in the late 2030s or early 2040s. And when it does, Voyager 2 will be in the same region of space it occupies today, barely a step beyond the Sun's doorstep on the scale of the galaxy. Its power supply will fail in another decade or two, ending our ability to communicate with it. But the spacecraft itself will endure. Silent and dark, yes, but still traveling, still existing, still carrying evidence of the civilization that built it. Ross 248, in 40,000 years. Sirius, in 296,000 years. The merger of the Milky Way and Andromeda in 4 billion years. The death of the last stars in trillions of years. These are the milestones of Voyager 2's future. Not endpoints, but waypoints on a journey that has no end. The spacecraft will continue existing until the universe itself changes so fundamentally that the concept of a trajectory, of motion, of existence becomes meaningless. That could be trillions of years from now, or longer. We don't know. But we know Voyager 2 will be part of that future, whatever it holds. A small piece of human ingenuity drifting through the cosmos. A messenger from a world that once looked up at the stars and dared to send something out into the dark. Tonight, we followed a spacecraft on its journey through the outer solar system and into interstellar space. We watched it visit Jupiter, Saturn, Uranus, and Neptune. We saw it cross the heliopause and enter the space between stars, We calculated its trajectory into the far future, to its encounter with Ross, 2, 4, 8 in 40,000 years, to its passage by Sirius in hundreds of thousands of years, to its eventual fate billions of years from now. Voyager 2 is still out there, right now, moving at 34,000 miles per hour through the darkness. It's the farthest human-made object from Earth that's still communicating with us. Soon, it will go silent. But it will continue its journey, carrying its golden record, traveling through the galaxy for billions of years. It will outlast the Earth, the Sun, and perhaps humanity itself. It represents our curiosity, our ambition, our hope that we might leave some mark on the universe. And in 40,000 years, it will pass Ross 248, a star most people have never heard of, as a ghost, dark, silent, carrying a golden record no one will play. That is what follows after the final place. Not a destination. An eternal drift through a galaxy that will never know it was there. Thanks for joining me on this exploration of Voyager 2's incredible voyage. The spacecraft may go silent soon, but its story, its mission, its message will continue echoing through the cosmos long after we're gone.